The raw power of heat is utilized down to the molecular level by rearranging the elemental structure of the metal, turning a coarse block of metal into a functional tool like a knife or a fork. Here at the blacksmith in Oakland's Crucible, they do just that. In this demonstration, we give a general overview of how a blacksmith transforms a block of O1 steel into a shiny cutting knife. This is the forge. It's the oven that cooks the metal to over 2000 degrees Fahrenheit and breaks down the crystal structure of the steel. The basic structure consists of a cast iron pipe with holes punched into it. This allows for natural gas and air to pass through, which ignite the intense flames from within. As the flames shoot out of the holes, they bounce against and around the interior walls like a vortex, which minimalizes heat loss. It is also aligned with castable refractory, a material similar to cement, which is very good at holding heat. This is displayed by the orange glow, its incandescent color. Now we insert the block of steel and begin the steel heat treating process. When an object is heated, its atoms expand and become less stable. When the molecules are spread apart, the blacksmith can take advantage of the weakened state of the metal and mold it into the desired shape of the knife. So what exactly is happening to this block of steel as it is being heated to such extreme temperatures? Well, steel is an alloy consisting primarily of the elements iron and a small ratio of carbon. As you let the steel heat up, carbon begins precipitating away from it. Generally, steel has about 2% or less carbon content. Although minute, carbon has a great impact on the crystal structure. At lower temperatures ranging from 1335 degrees Fahrenheit and below, the steel will exhibit the crystalline form of pearlite. In this state, the steel has very high strength, hardness, and toughness. We aim for a good middle ground combination in the final product. The atoms will not be too hard or soft, but just right. Pure iron with a carbon percentage of 0.8 or less has the structure of ferrite, which gives the steel its magnetic properties. Iron carbide exists when the carbon percentage is 0.8 or more and exhibits cementite. It is a hard, brittle material and is essentially a ceramic in its pure form. Although this combination of pearlite makes for a good final product, it is not soft or workable enough to shape the steel into the knife. The steel and its atoms will need to be manipulated further. Once the steel surpasses 1335 degrees Fahrenheit, it hits the critical temperature. From this point on, the steel takes on the crystalline structure of austenite, along with the possible mixtures of ferrite and cementite. Austenite is easily manipulated at extreme temperatures and resists corrosion. Of course, these are ideal conditions to shape and mold the once rigid steel. When heating the steel in the forge, reaching the austenitic phase is the goal. Alright, let's head back to the blacksmith and check on our steel. As we wait for the steel to reach the critical temperature, let's review the tools that we will use to mold the metal into the knife. This is our blacksmith, Skylar, and he will be demonstrating the entire process for you. These are 1.5-inch box tongs to grab the pieces of steel. This is a German-style, round-face cross-peen hammer. The round face allows the strike from the hammer to move and distribute the material surface. These kinds of strikes are good for bigger areas and general shaping. For more specific and detailed strikes, the blacksmith uses this flat-faced hammer. The difference here is that the strikes are perpendicular and will have more equally distributed deformation. They would be used to get the finishing touches or refine the shape. Now that we have seen the basic tools used in blacksmithing, let's see Skylar put them to work. After the steel has been heated to the critical temperature, the blacksmith can taper or hammer it down to the desired shape. It is a long and arduous process and takes extreme precision and patience. The blacksmith continually strikes and compresses the softened metal on the anvil. Applying Newton's second law of motion, the anvil gives an equal and opposite force reaction to the downward strikes from the hammer, squashing and compressing the steel together in the middle. Time is of the essence as the steel quickly cools down. Unfortunately, you cannot just simply keep reheating it by throwing it back into the forge. Each time you do so, the steel is being weakened. The more you cook it, the more likely the steel is to shatter. Once the blacksmith has done as much as he possibly can to the softened steel, a machine is brought in to finish the tapering process. This is the power hammer. It is used for precise and heavy work. It slams down an 88-pound hammer upon the metal, which is significantly larger than the handheld one. Not only does it have immense strength, but also extreme precision. It appears that steam is being vaporized from the steel as it is being crushed. However, that is actually oil vapor burning up from the dripping oil of the machine only. After the long and tedious process of shaping the steel into a knife, it is finally time to firmly seal the crystal structure back into place. After putting the knife into the forge one last time to loosen up the squashed atoms and crystal structures, its composition is tested by touching it against a magnet. If it sticks, the steel has the pearlite crystalline structure because of its magnetic field, and thus it's below the critical temperature of 1,335 degrees Fahrenheit. We can see that the magnet does not stick and thus is austenitic steel. Since the steel has passed the test, it can be cooled down in the process called annealing. The knife is placed in a bucket of sand to cool. It will cool at a much slower rate compared to room temperature or other methods, such as quenching it in water or oil. Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the temperature of its surroundings. Air bubbles are trapped in between the grains of sand and insulate the heat radiating from the hot steel. Thus, it slows down the cooling process considerably. If we instantly cool off the red-hot steel at this point, a new crystal structure, martensite, would be created. Martensite is characterized by an angular needle-like structure with extremely high hardness. However, it is also extremely brittle and will break upon contact. Internal stress occurs from such an extreme and quick phase transformation. Despite martensite's rigidity issues, our steel must actually take its form. Cooling it off in the sand just relieves the intensity of the extreme deformation. The steel is then quenched in a bucket of oil to compact the molecules all together and quickly finish the cooling process. Because the steel is still martensitic, the knife will probably break with minimal pressure, making it virtually useless. So the steel needs to be recrystallized through the process known as tempering to toughen it up. This process requires reheating this newly created martensitic steel in select areas to bring some ferrite and cementite structures back. Although extremely less hard than its current state, it will be considerably much tougher. A new block of steel is heated to roughly 800 degrees Fahrenheit and will be used to spot heat and to form the knife once again. Meanwhile, the knife is being sanded down to remove as much of the oil from the surface to reveal the shiny new steel underneath. Tempering relaxes the molecules again, but not nearly as much as annealing does. It keeps the piece from being too brittle. After this, it will be just right, not too hard, not too soft. Steel exhibits different colors depending on the temperature. Temperatures above 800 degrees Fahrenheit produce incandescent colors. This is displayed by the amazing orange glow from the steel block. The atoms in the steel are so energized by the heat that they give off photons. Temperatures below 800 degrees Fahrenheit produce oxidation colors. As the steel is heated, an oxide layer actually forms on the surface. Its thickness, and thus the interference color as light is reflected, is a function of temperature. So you can actually see the temperature at which each portion of the steel is being heated to. Once the tempered steel turns gray, the blacksmith knows that the critical temperature is being surpassed and needs to stop. It should never go above the critical temperature because it will enter the annealing heat stages again, and thus relax or spread the molecules out too much. Once again, this is simply a demonstration, mostly to see the wide range of oxidation colors. The warped colors on the knife would ideally be a solid one for a finalized product. Once the steel is done being tempered, the knife is tough and hard enough to be sharpened, polished, and finalized. And that is the entire steel heat treating process that turns this ordinary block into this final knife.